Hello, this is R-Nasrinov. I'm presenting edge-based vibration anomaly detection. This is based on a paper that I wrote. And so I realized that the presentations were supposed to be on Thursday in person, but because I kind of messed up the timing and my internship starts on Wednesday morning, I was hoping that this or some other form of remote presentation could be accepted instead. And getting right into it, so why Edge AI use case like for anomaly detection based on vibrations? Well, first of all, because for companies that have these machines that we're kind of targeting, they could be either in remote locations where it'd be inconvenient to send the data to a server, or otherwise the company may not want to send operational data to an outside server for compute for privacy reasons. It's also a pretty interesting problem because vibrational signals are pretty high bandwidth, and so reducing that is an interesting challenge, but also something that's very, very well explored. And I guess the target is to be able to eventually run it on a ESP32, and I believe like with the current model size, it's already something that's feasible. So we'll get right into that. Then the next thing I guess is some literature review. Ahmed et al. Had some great success using autoencoders for kind of a similar application. Very, very high F1 score, obviously, but they use LSTM and CNN layers, which means that their model was pretty heavy. But then our synergists did paper where they used TinyML for spectral analysis. And my paper is kind of building on that, and with the focus being on k-means anomaly detection with a very small footprint, just being 239 bytes, without kind of losing the ability to discriminate between normal and faulty states. We basically want the model to actually work. And I guess the next thing is the technical dataset profile. The dataset that I use is the Fraunhofer rotating shaft dataset. It's evaluated to basically shaft and unbalance at different strengths, and it has like these conditions, events, and you can see the different Windows features. So the important thing is that the model is trained and calibrated fully on normal balanced data, and then it's tested against like failures, and the rationale behind that is in the real world, it's very expensive to like break a machine on purpose just to get the data of how it fails. Instead, the better goal is to be able to like look at the normal regime, and then when there's a failure to be able to identify it just based on what's normal. So the spectral feature extraction is pretty crucial here in minimizing the model size, because instead of feeding like 4,000 raw vibration samples into the model, I first summarized each signal using frequency-based features, and then that told me where the vibration energy is concentrated and how the vibration pattern is distributed across these frequencies. And then I compressed this information into the 7 features seen here, and the centroid features I'm missing, but I use that, so just the average. And it's allowed me to keep the computation small enough to have it be on an embedded device while still being rather effective. So the pipeline, I guess, is that once the features are extracted, they move in kind of 3 stages. First, the system checks whether the machine is running. This saves a lot of compute because you don't want to be running analysis on something when it's off, really. If not, then it ignores this window and it extracts and prepares the vibration features for the model. So once the model is on, you want the vibrations. And the last thing it does is basically just applies a simple voting rule that requires multiple abnormal readings before raising the alarm. So if it's just like one abnormal reading because of some weird temporary problem, it won't cause an alarm. But if it's 2 in a row is the current threshold, then it will raise that trigger. So the next thing, I guess, is explaining k-means anomaly scoring. For anomaly detection, the model first learns what normal vibration looks like from healthy machine data, and then when the new data arrives, it looks at how far that vibration is from normal behavior. If the difference is large, then as you can see, the system flags it as an anomaly. Since this is like a pretty simple calculation, it's pretty cost efficient as well. And then I guess the comparative analysis here is we compared it against a basic RMS energy threshold, and it was pretty clear. As you can see, the data supports that the spectral k-means model was a lot more effective. The RMS method pretty much missed almost everything except like the most extreme imbalances, and our model, on the other hand, was pretty good. I mean, not like perfect, but when it's a strong signal, it was correct about 86% of the time. And that's because it captures frequency shifts that are invisible. Basically, it's a simple time-based energy metric. So, yes, the next thing to discuss would be feature ablation and efficiency. I ran a few studies, starting with a full like 16 feature set, and that gave me an F1 score of 0.826. And actually, what I found that trimming it down to just 7 spectral features, the F1 score improved, and that's because the features were carefully selected, basically. And I tested that over a bunch of different iterations, and that still held. I mean, it's not a huge difference. The fact that we can cut down on the number of features and still improve the F1 score is pretty big. But then if you cut it down anymore, it does go down. So 7 was found to be the kind of golden number. So then the resource footprint here, quantizing the model to like in age shrinks the RM like pretty significantly, just 56 to 239 bytes. So it's like pretty good. It's also not that much of a difference because it's all just in bytes at the end of the day. But the kind of true bottleneck here isn't kind of the model itself. It's the SRAM required for an 8 kilobyte signal buffer and the 16 kilobyte FFT workspace. So I guess the next thing to discuss would be the streaming analysis, which is kind of, you can see the system evolve over 80 seconds. You can see that the activity gate kind of keeps it all at 0 because the machine isn't active. But then as soon as the imbalance is introduced, you can see that the anomaly score jumps, and then like when the imbalance is very strong, you can see like it's pretty accurate. But like down here, it's not that good, but it's still pretty decent. All right, so I guess the last thing is the takeaways. What we can conclude is that the project demonstrates that a k-means model can, in fact, effectively detect vibration anomalies on kind of source constrained devices, and it also shows that the final model in conclusion was like pretty good. It had some strong detection performance and only required a few hundred bytes of storage. So it's pretty practical for a low-cost embedded system, and reducing the model by like 4 times through the process of the design had almost no impact on accuracy, which is a very interesting takeaway, and just goes to show that TinyML is a suitable application for this. I guess next steps would be to actually code it up in like C, C++, get the optimized code going, which is challenging in of itself, but get it on ESP32 or some real microcontroller. And yeah, that's pretty much all I had. Thank you very much. These are my answers.